Hi everyone, welcome back to Core and Code. This is part 3 of our UART communication series between STM32 and Raspberry Pi. In the previous video, we configured the UART peripheral using STM32 CubeMX. In this video, we will go through the STM32 code in STM32 CubeIDE and understand it step by step. Now I am opening STM32 CubeIDE and my project. First, let's look at the project structure. Inside the core folder, we have src, which contains our main source file, main.c. We also have the inc folder, which contains all header files. Now let's open main.c and start writing the code and understanding it step by step. Now we will start by including the required header files. First, we include main.h, which contains all STM32 peripheral definitions and configuration. Next, we include string.h because we are working with strings like string length. We use string length to calculate the length of the message before sending it through UART. Now I am scrolling down and going inside the main function. Here we can see the initialization functions. First, we have HAL init. This initializes HAL library and prepares the microcontroller to run the program. It also sets up the system timer used for delay. Next, we have system clock config. This function configures the system clock frequency and decides how fast the microcontroller runs. Both HAL init and system clock config must be initialized first before using any peripheral. After that, we have mxGPIO init. This function initializes the GPIO pins. It configures pins as input or output based on our configuration. And finally, we have mxUART1 UART init and mxUART2 UART init. These functions initialize the UART peripherals. They set parameters like baud rate, data bits, stop bits, and mode. After this, UART communication becomes ready to use. UART1 is physically connected to the Raspberry Pi and UART2 is connected to the PC through ST-Link. This allows us to communicate with the Raspberry Pi and view the output on the PC. Now I am declaring a variable called rx, which is used to store data received from the Raspberry Pi. Next, we have debug message, which is a character array used to store the message and then transmit it to the PC using UART. This is an infinite loop, which means code inside this loop will run continuously. Here we are using the polling method, where the microcontroller continuously checks for data to send and receive. Now I am creating a message that we want to send from STM32 to Raspberry Pi. After that, I am using the HAL UART transmit function to send this message. HAL UART transmit is a HAL function used to send data through UART. The first part selects the UART we are using. Here, UART1 is used, which is connected to the Raspberry Pi. The next part contains the message that we want to send. We typecast it because UART communication works with data in bytes. After that, we calculate the length of the message. This helps UART understand how many bytes needs to be transmitted. The last part makes STM32 wait until transmission is completed. This means the function will not time out. So in simple words, this line sends the message from STM32 to Raspberry Pi using UART1. HAL UART receive is a HAL function used to receive data through UART. Here we select the UART connected to the Raspberry Pi. The received data will be stored in the RX variable. This value tells STM32 to receive 1 byte of data at a time. This value defines the timeout, meaning STM32 will wait for a short time to receive data. If data is received successfully, the function returns HAL OK, and the code inside the if condition will execute. Here, we use sprintf to create the message. The message is stored in the debug message array and includes the data received from the Raspberry Pi. This message will be printed on the PC terminal. This transmit function works the same way as the previous one. The only difference is that here we are using UART2, which is connected to the PC through ST-Link. This selects UART2 for transmission. This contains the message stored in the debug message array. Here, we calculate the length of the message, and this makes STM32 wait until the transmission is completed. So, this message is sent from STM32 to the PC and displayed on the terminal. This way, I can see the reply received from the Raspberry Pi. Here, I am adding a 1 second delay. This helps prevent continuous flooding of messages. It also makes the output much easier to read on the terminal. And this closes the while loop, so the entire process will keep repeating continuously. So, the flow is simple. STM32 sends a message to the Raspberry Pi. Raspberry Pi receives it and prints it on the terminal. Then Raspberry Pi sends data back and STM32 receives it and displays it on the PC. This confirms that UART communication is working. In the next video, we will see how this communication is done from the Raspberry Pi side using terminal commands through Putty. Now I will build the project. Next, I am opening the debug configuration. Here I am going to the debugger settings. I am keeping the required options and checking SWV. SWV is used to view debug output while the program is running. Now I am applying the settings and starting debug. You can see the board LED blinking while the program is flashing. This means the code is getting loaded into the STM32. Now the flashing is completed. I am clicking here to switch to the debug terminal. And that's it for this video. In the next video, we will continue with the Raspberry Pi site, where we will use terminal commands using Putty and view the output on the PC using teraterm.